Here we go with iChem lesson 8 on ionic bonding and writing formulas. Make sure you have your viewing guide in front of you. There's a few examples that we're going to go through in addition to the notes, and you should have it all down by the end. So first, a quick overview. We already know a little bit about this stuff that will help us write the formulas. So first, we understand this idea that most neutral atoms are unstable. Maybe we haven't put it in those terms, but we know that almost all atoms need 8 valence electrons to be considered stable. We know that metals lose electrons to become stable, so metals have positive ions. We know that many nonmetals gain electrons to become stable, which is negative ions. And also, we haven't really talked about this, but nonmetals can share electrons to become stable. This sharing will come into play more next week. Today we're going to talk about sort of the part 1, which is ionic bonding, where metals are bonding with nonmetals. It involves losing electrons and gaining electrons to form ions. Covalent bonding involves the sharing. We'll talk about that next week. And it's nonmetals and metals. So if you just kind of think about these definitions, you can recognize something that would have an ionic bond as something that would have a metal in it. So here's our first example. We have a sodium and a chlorine atom. The sodium atom, we know, will lose an electron to become stable, uncovering that full outer shell underneath. Sodium, we know, will gain an electron to become stable. It has 7 valence electrons. It wants one more. It'll take that electron from sodium. We could think about it in terms of electronegativity also, chlorine being a whole lot more electronegative than sodium. It's more likely to take the electron in a bond. We also know that opposites attract, so the positive sodium ion and the negative chlorine ion are bonded by a force of attraction, and they become NaCl, or sodium chloride. Notice that the overall charge of the compound is neutral. In ionic bond, this is a common theme. Positive attracts negative to make neutral. +1 and -1 cancel out. They're 0. So let's do a few more examples. I have magnesium and nitrogen. I know that when it forms ions, magnesium is a 2+. It's in that second column, second group of the periodic table. That whole group forms ions with a +2 charge. Nitrogen, on the other hand, is in group 5. It has a -3 charge when it forms ions. So I have my 2 ions here now. They're going to attract each other and combine in such a way that they make a neutral atom. So let's just combine them together. If I had magnesium, don't write this because that's not right, and nitrogen, would it be neutral? I have +2 -3. That's equal to -1. That is not a neutral compound. That is not the correct formula. What you do is you look at the charge. I have 2 and I have 3. I'm going to do what I call swap and drop. The 3 is going to drop down and go to magnesium. The 2 is going to drop down and be paired with nitrogen. What this looks like is magnesium with a subscript that's a 3. The 3 swapped and dropped. And nitrogen with a subscript that's a 2. what this means is I have 3 magnesiums bonded together with 2 nitrogens. Let's see if that makes a neutral compound. I have 3 magnesiums, each of them a positive 2 charge, and I have 2 nitrogens, each of them having a negative 3 charge. Here I get positive 6, here I get negative 6, which is in fact neutral. Notice though a simple 1-to-1 ratio of atoms doesn't address the need of each atom as simply as sodium and chloride. You have to have the ratios that allows you to have a neutral compound. Let's do another one. Calcium. We know that calcium is 2 plus. Second column of the periodic table. This should start to become second nature to you. We know sulfur is 2 minus. If I follow my rules, I have a 2 here and a 2 here. I'm going to swap and drop. 2 and 2. I have calcium with a 2 as a subscript and sulfur with a 2 as a subscript. I have 2 calciums with a positive 2 charge, and I have 2 sulfurs with a negative 2 charge. That is indeed neutral. However, this isn't the lowest combination that would satisfy this. These are both 2. I can divide both subscripts by 2. You get calcium and sulfur. 1 calcium, 1 sulfur. 1 calcium with the 2 plus charge plus 1 sulfur with a minus 2 charge still gives me 0. So whenever I have a common factor here, a 2 and a 2, I can factor that out and simplify the formula. Let's do one more. I have aluminum and chloride. Aluminum, I know from its position on the periodic table, is a plus 3 charge. Chlorine, I know from its position on the periodic table, is a minus 1 charge. We don't normally write the 1, but for the purposes of writing the formula, I think it helps. So I have a 3 and a 1. I swap and drop. Aluminum, and I have 1 of them. Chlorine, and I have 3 of them. Prove to ourselves that it's neutral. 1 aluminum with a plus 3 charge, and 3 chlorines with a minus 1 charge. That's a 0 overall charge. Now this 1 right here, I put it there just to show you the process, but the final formula would be more appropriately written as AlCl3. We don't, in chemistry, write 1s. We don't write the 1 necessarily in the charge, and we don't write the 1 as a subscript, but as you're starting, if it helps you, go ahead and do it. Okay, so let's look at the steps we followed. The first step was to write each ion with appropriate charges. The second step is to swap and drop the charges. Now we always write the cation first when we're writing them out so that the formula has the cation, then the anion, in that order. The next step, number 3, you look for a greatest common factor. Can I divide the subscripts by something that will simplify the formula? And then you check your work, make sure that it ends up with a neutral charge. If you flip over to the back, we're just adding 1 level of complexity to this, and this is the idea of a polyatomic ion. It's an ion composed of 2 or more atoms that can be considered to be acting as a single unit. Acting as a single unit is underlined in bold there. They're considered all 1 ion, so we never, ever, ever break these up. I'll show you what I mean. You have this table of them on your notes. This will become, and it's on the back of the periodic table that you have already as well. You'll need this just like you need the periodic table from this point forward. So I have aluminum, I know from its position on the periodic table, is a 3+. Sulfate is a polyatomic ion. I know it's a polyatomic ion because of its name. It ends in ATE. So I look at my table, polyatomic ions, and sulfate is SO4 2-. Now by definition, the polyatomic ions stay together. To help you remember it needs to stay together, put parentheses around it. Now, I swap and drop the same way. 3 goes there, 3 goes there, 2 goes there. I end up with Al2. SO4 stays in parentheses, and a 3. Let's do another one. Calcium, 2+. Carbonate, ATE, helps you notice that it's a polyatomic ion. I look on the back of my sheet. I find the carbonate ion to be this. I'm going to put it in parentheses so I know I don't break it up. And when I swap and drop, 2 goes down, 2 goes down, I end up with Ca in parentheses CO3. And both of them have a 2 as a subscript. But I don't need to keep that 2 there. I can factor it out. Divide both subscripts by 2. I get Ca. Oops. CO3. Notice I don't have the parentheses here anymore. You can keep them if it helps guide your eye. When there is no subscript outside the parentheses, you would no longer need it. The final formula should always be neutral. Let's do one more. Sodium, we know Na+ from its position on the periodic table. Hypochlorite ends in ITE. That helps you know that it's a polyatomic ion. I find it on the back of my periodic table. I have 1 and 1 here. I don't write them, but I know it's 1. When I swap and drop, I have 1 and 1 again, and we don't write the 1s. NaClO. I want you guys to try magnesium and phosphate on your own. There's a space in your notes for that. I will ask you for it on your Google form. So in summary, all final formulas must be neutral. So check for that, especially when you were first starting this. It's good practice. No subscripts or charges appear, superscripts, sorry, no superscripts or charges appear in your final formula. There should be no plus, there should be no minus, there should be nothing written above the element symbol, bottom right corner only. And you always want to reduce your subscripts in the final answer. So if you can cancel out a greatest common factor, do so. But never change anything in the polyatomic ion. Keep it in parentheses to help guide you. But you do not need
Sarah Painter, please come to the school counseling office. Sarah Painter to the school counseling office, please.
Sorry. You do not need parentheses around the polyatomic ion if there's no subscript. But keep it there if a subscript ends up on the polyatomic ion. We'll do a lot more practice with this in class tomorrow. Be ready to party. Yeah, we should.
please report to admin 2. Jocelyn Melvin, please report to admin 2.